name, both our ionic and covalent compounds, we can think about how we can weigh them out. And so, much like individual atoms having their defined mass that we can find on the periodic table, we can do the same thing for the mass of our compounds. And the term we use for the mass of our compounds is the formula or molecular mass. And it is simply defined as our defined mass of compound. And in order to calculate that, there are molecular or our formal mass. We're just going to take the sum of the atomic masses. And so the way that we'll calculate this is using a kind of scheme just like this, where we'll find the number of a element in whatever we're looking at. We're going to times that by the atomic mass of that element. And then you're going to do that so on and so forth for however many compounds you're looking at. And so let's say, for example, we're talking about something like CO2. So you have CO2, and we can say, let's say our first atom is carbon and our second atom is oxygen. We'd look up their atomic masses. For carbon, that's 12.01 1 AMU. And for oxygen, that's 16.00 AMU. And you can do that. You can say I have one carbon, and I'm going to multiply that by its atomic mass of 12.011 atomic mass units. And then to that, I'm going to add, and I'll switch colors to green here just to match the scheme we have above, the two oxygens I have, because we have, our two oxygens right here, multiplied by their atomic mass of 16 AMU. You go ahead and you multiply that all together. And what you would get is that for CO2, we would say that the molecular mass, because CO2 is a molecule, it's a covalent compound, is 44.011 AMU. That's for CO2. We can also do a ionic compound, something like sodium oxide, so Na2O, which when I say sodium oxide, you should be able to tell how many sodiums and how many oxygens you have when writing that formula. But we know we have two sodiums. Each of those sodiums weigh 22.99 atomic mass units. You add your single oxygen, so 1 times 16.00 atomic mass units. You sum that together, and you'd find that the formula weight for sodium oxide is 61.98 atomic mass units. So we'd say this is a formula weight because we have an ionic formula. This one is a molecular weight because we have a molecule. And then just as one final example, let's say we're looking at something like barium nitrate. And so another one that you should be able to figure out, that barium is a 2 plus charge, and we know that the polyatomic of nitrate, which I'll just write off to the side, NO3 minus, has a single minus charge. And so when you're matching those up, if you want to have charge neutrality, in order to cancel both the positive charge from the barium, your nitrate is simply going to be, in parentheses, we'll have the N. And I'm just going to do different colors so that we can do each of the different colors as we do these masses. O3. I'll close the parentheses, and we'll put a 2 here because we need two nitrates to balance out the charge of barium in order to give you our compound here. And if we were to do the formula weight for this, we're still going to do the same thing, but we're going to be very intentional about how we do this. So we have one barium. We look up its atomic mass, and that'd be 137.3 AMU. We then add to that our mass of nitrogen. And so we can see nitrate is contained in, these parentheses, and it's being multiplied by 2. So that means everything inside the parentheses is multiplied by 2. So we have a single nitrogen multiplied by 2. So that's two nitrogens with their atomic mass of 14.01 AMU. And then we have our oxygen, which we have 3 oxygens that are part of nitrate. So we'll put a 3 here. There's 2 nitrates for this compound, so we'll put a 2 here. And then we'll multiply that by the molecular weight of oxygen, 16.00 AMU. And, just for clarity, if we want to match the colors, we can make this to that light blue color to match the 2 that we have as a subscript. And then our total mass here for barium nitrate is going to be 261.3 AMU. And so all of these, I'm just showing a couple different calculations here. The important part is just knowing how to use this formula right here that just says find one of your atoms, find out how many of those atoms you have, multiply by its atomic mass, do the same thing for everything else. And this tells you the mass of a single one of those molecules or formula units. If instead we want to talk about a manageable size, then we're going to talk about um, things called, the molecular weight. And so the same way that when we talked about weighing out a mole of atoms, we talked about its molar mass rather than its atomic mass. Here we're going to talk about the molecular weight or the formula weight for each of these different compounds. And so before we said that, when you're calculating the atomic mass, or sorry, the weight of 1 mole of something like carbon, we know that carbon weighs 12.011 atomic mass units. This was 1 carbon. And then when you talked about 6.022 times 10 to the 23rd carbons, we said that that weighed 12.011 grams. And that was grams per mole of carbon. So we can do the same thing for our formula units and our molecular compounds. And so for 1 mole of molecules, we're going to say its mass is equal to that mass in grams relative to its weight in atomic mass units. And so 1 mole of CO2, which initially we said weighs 44.01 AMU, it weighs 44.01 grams. And so we'll define the term that, talks about this weight in grams of a molecule or a ionic compound as either the molecular weight or the formula weight. So before we were talking about molecular mass and formula mass corresponding to only one of something. When we use weight, we're going to talk about 1 mole of something. So this is the mass in grams of 1 mole of a given molecule. And like we said, it's equivalent to its weight in atomic mass units. And so before we had a scheme that looked like this, where we said in order to go from mass to moles, we used our molecular mass, this was our molar mass. And then to go from moles to atoms, we used our Avogadro's number. Now we're going to add 2 more things. We're going to add the molecular weight. This is your molecular weight. So the weight of a molecule. Or the formula weight. And this is the weight of a formula unit. All of those can be used to go from mass of something to moles of something. And then as we go from moles to atoms, we're also going to be able to not only go to atoms, but we're going to be able to go to the number of a specific molecules or ions or formula units. So all of these things can utilize the same conversion factors that we've talked about before. And so let's see what one of those such calculations looks like. We're going to be talking about calculating for us the molecules of CO2 that are exhaled in the 1 gram total of gases that are exhaled in every breath, knowing that CO2 makes up about 3.8% of that mass. And so if we're going to solve this, we'll do our 4-step process that we always do, and that starts with writing down what we know. So what we know in our sort part is that you have 1.0 grams of gases. CO2 is 3.8% of that mass, and we know that the molecular weight of CO2 is 44.01 grams per mole. And then we're going to write down what do we want. We want our atoms of CO2. And so in terms of our strategize, if we know we're starting with a mass in grams and we want to end up at atoms, we can just use that roadmap that on our last slide to tell us how we're going to get from A to B. So we'll start with the mass of a breath, because that is all gases. And then we're going to move towards our mass of CO2. And from there, we can just use our normal conversions. And so it starts by taking these 2 pieces of information to find out how much CO2 you have. Then the rest of it is, carried forward for CO2. So mass of CO2, moles of CO2, ending with our molecules of CO2. And so if we go ahead and do that math, we'll take that 1 gram of gases exhaled, we'll multiply it by that percent by mass of CO2. So for every, this 3.8% means that for every 100 grams of gases, there is 3.8 grams of CO2. And that ratio is 3.8 G CO2 for 100 grams of gases. So we do that, right here, I put grams exhale instead of grams gases. You're going to divide by the molecular weight, 44.01 grams. And for our purposes, we can get rid of that moles because that's what we have on top. So you divide by the 44.01 grams. You're going to multiply it by Avogadro's number that says that there's 6.022 times 10 to the 23rd molecules of CO2 per mole of CO2. And you end up with an answer like this. You have 5.1996 times 10 to the 20th molecules. And we're going to bring that down to 2 sig figs because you have 2 sig figs right up here for your mass of 1.0 grams has its 2 sig figs. And so that's how you can do just conversions of, I have a molecule, I have a certain mass of that molecule, how many atoms do I have? That's a pretty straightforward process. But what if we also want to think about going from a certain amount of molecule to find out how much of an element there is in that molecule? So if you have a certain mass of CO2, how much oxygen do you have? Something like that. And so the first thing we're going to do in these processes is we're always going to determine the moles of the compound, because from there we can do a lot of easy interchange. If we started only at mass, we're going to see that that's going to be a problem because your compound and your element have different masses. And so let's say we're, like I mentioned before, we're trying to find out how many oxygen atoms were exhaled in that CO2 we talked about on the last slide. This number of molecules of CO2 we have here, where in this first step right here, we calculated the number of moles. Excuse me. So if you take that answer from taking that 1 gram of exhale, times it by our percent by mass of CO2, then dividing by the molecular weight of CO2, you'd end up with your moles of compound. So that's what we've done right here. And you'd see that we have 8.6 times 10 to the negative 4 moles of CO2. The next thing we're going to do is we're going to multiply that number of moles by the amount of individual element in that compound, something called the molar ratio. And so we define that as the number of atoms of one species in a compound. And so if we're looking at CO2, what we're looking at is that in CO2, so for every 1 CO2, there is 1 carbon. And if we're looking at the oxygen, for every 1 CO2, there are 2 oxygens. Excuse me. And so if we can make this comparison of, for every 1 molecule of CO2, there's 1 carbon atom, we can extend that out towards how much a mole of each one of these things have. And so for every 1 mole of CO2, just changing from a single instance to 1 mole of that thing, you're going to have 1 mole of carbon. And for every 1 mole of CO2, you have 2 moles of oxygen. And so now what we see is we have things in terms of moles. This molar ratio, which basically compares, when I say number, I'm just saying moles of atoms of one species in a compound, and I'm saying moles of that compound. We can utilize that with the mole amount we've calculated right here. You see you have, and I'll even highlight it, you have mole CO2 right here, you have mole CO2 right here. And so you can do a conversion now. Sorry, not laser pointer. We'll go to pen. You can do a conversion here where you say those 8.6 times 10 to the minus 4th moles multiplied by this ratio. We said that for every 1 mole of CO2, there's 2 moles of oxygen. You can make that into the ratio of, what we have below, because this is effectively the same as saying 1 mole CO2 ratio 2 moles of O, and then you make this conversion factor right here. You end up with the 1.72 times 10 to the negative 3rd moles of oxygen. And then from there, if we're trying to figure out, how many atoms we have, we can just continue on with our normal conversions. In this case, we could multiply by Avogadro's number, and you'd see that in that exhaled breath, there is 1.0 times 10 to the 21st atoms of oxygen. And so that's a very formal way that we can do these types of conversions. But what's also nice is we can take a little bit of a shortcut. Once you have found the number of molecules, so the number of CO2 molecules, so the answer we had 2 slides ago, you can also take that number and multiply it by the molar ratio as well, saying that if you have 5.2 times 10 to the 20th molecules of CO2, and we'll put in red, this is molecules of CO2, you multiply that by the 2 oxygens contained in there, you get the same answer. And so when you're doing these types of conversions, you can go to the amount in moles, which is going to be our most common unit, and I'll box it here. I'll also grab my laser pointer. You can go to your amount in moles and then use that molar ratio that takes advantage of the chemical formula to find the mole of the element and then convert to, number of molecules or a mass. Or you can go down to molecules and then use the chemical formula to find out the amount of the element in the compound. In this case, it wouldn't be in terms of moles anymore. It would be instead in atoms. The important thing is that we cannot do this direct comparison of mass to mass, because the mass of CO2, it has a mass of 4.01 grams per mole, or AMU, whatever unit you want to use, whereas oxygen has a mass of 16. And you can't just say 44 times 2 is equal to 16, because we know that's not true. You have to go to, in this case, your amount, because then you can do a lot of common conversions. Because now that you're in a number of things rather than a mass, because masses differ between the compound and the atom, the amount is, it's a common quote unquote unit we can use where it's easy to convert from one to another. Because you can say 10 CO2s have 10 carbons. You don't have to worry about 10 grams of CO2 has 10 grams of carbon, because that's not true. If we did want to do any direct mass to mass conversion, so mass of CO2 to mass of carbon, what we're going to have to do is utilize our mass percent, which is what we're going to do in just one slide. But before we do that, I'm just going to expand our conversion chart by one set of boxes. And so this is what we've seen before, this mass to moles to atoms, ions, or molecules, where we have molecular weight, molar mass, or formula weight. And what we're going to do is we're just going to add 2 more boxes. And so you can fill in one of your boxes, and this is just expanding on what I had on that last slide. So just showing our own version of this boxed element right here. So we're just reproducing that boxed element right there. And so we're just going to add a box where you can take advantage of the molar ratio to go from moles of A, most often moles of compound, or moles of element. Take advantage of that molar ratio that says how many of each element there is in a compound, and you get moles of, the other thing. We also said we can do direct conversions from atoms, ions, and molecules to the opposite of atoms, ions, and molecules. So you could start at atoms of oxygen, utilize the molar ratio, and get molecules of CO2. It's all the same. And so for the conversion we did previously, we looked at something like this. We took the mass of a compound, divided by the molecular weight to get moles of the compound, utilize the molar ratio, and I'll grab once again my laser pointer here, utilize the molar ratio to get moles of element, multiplied by its molar mass to get your mass of your element. So this is, I guess technically we didn't do mass of element on the last slide, we actually went to atoms, but this is the conversion if we tried to go from mass to mass, where there would just be one more box here where we'd go mass of B. So you can see this is a little bit of a process. You have to go from mass to moles to back to mass. So let's talk about shortcutting it using that mass percent I talked about on that last slide. And so as you might recall, when we talked about our law of constant composition, we said that, always a compound is composed of the exact same elements in the exact same relative ratios. And we calculated something called a mass percent, and we said that this is the fraction of mass that comes from a single element. We calculated it by finding the mass of element X in a compound, dividing by the total mass of the compound, multiplied that by 100%, and we looked at a couple percentages. We talked about, CO2 is like 25% carbon and 75% oxygen. So now let's actually do a couple of those calculations ourselves, where, our conversion of this to kind of units that might be more familiar to us is we're going to take, to calculate mass percent, we're going to take the number of atoms of whatever element we're looking at, multiply it by its atomic mass in AMU, and then divide it by the total molecular mass / molecular weight, or I should not cross this out, but just say or formula. So either the formula weight or the molecular weight. So in this case, it's a mass because we're just talking about things in AMU. But if you wanted to instead talk about, things in terms of grams per mole, you can also do the same thing, but in this case, instead of molecular mass, this is going to be molecular weight. So do this however you'd prefer. It's probably easiest to do the former, where we just focus on the masses of things in AMU. So we're going to look at doing an example of this. So let's ask ourselves, what is the mass percent of each element in ammonium nitrate? And so this starts by utilizing what we just talked about for determining the formula for, in this case, you'd look at this and you could ask yourselves, is this an ionic or a covalent compound? And we'd see that these are two charged polyatomics, and they're joined together by an ionic bond. So we'd say, this is an ionic compound. Its formula is NH4NO3. And since part of doing this calculation means you need to know the formula mass of the compound in this case, we calculate the formula mass by, counting the number of nitrogens we have, multiplied by their atomic mass, the number of hydrogens, and the number of oxygens. And what we'd end up with is a formula. In this case, it shouldn't be the formula weight, but instead it should be the formula mass, because we're only talking about one of these. And the exact terminology of mass versus weight, don't get too caught up in. And then we can just calculate the mass percent for each one of these. For nitrogen, we know there's 2 nitrogens. We multiply by the mass we find on the periodic table for nitrogen of 14.01. And then we divide it by the formula mass we just calculated. We find out that nitrogen is 35% of the mass of ammonium nitrate. You go on and do that for hydrogen. You have 4 hydrogens, multiply by their atomic mass. And then finally, you do that for oxygen. And so you get these mass percents. And this is, these were percentages we saw before, and we talked about doing a couple of conversions utilizing these in the first chapter of our textbook. And so let's see how we can utilize these mass percents, because what's really awesome is you can use them as a conversion factor. And you can utilize them to determine the total mass of a compound, or when given the total mass of a compound, you can find out what mass of a specific element is part of it without going through all of the mass of compound to moles of compound to moles of element to mass of element. So here, what we're going to do is we're just going to solve this just like we would any other problem. So that starts with a sort. And in our sort step, what we know is that we have 22 grams, of NH4NO3, ammonium nitrate. And what we want is simply the mass of nitrogen. Okay, so that's our sort. We'll switch colors for strategize. I'll do this in purple. So for strategize, I know I'm going to start with grams of ammonium nitrate, and I'm actually going to be able to do this rather quickly. I'm going to go directly to mass of nitrogen. The way I'm going to do this, what I'm going to utilize is going to be the mass percent. And that's one thing that we forgot to add to our know, because what we know is that the mass percent, which I'll notate like this, mass percent of nitrogen is equal to 35%. And effectively, what that is saying is that there are 35 grams of nitrogen for every 100 grams of compound NH4NO3. Okay? And so let's go ahead and just do our calculation now. It's going to be a fast calculation. We'll say in our solve step, we'll say we have 22 grams of ammonium nitrate, NH4NO3, and we said for every 100 grams of NH4NO3, you have 35 grams of nitrogen. You multiply this on through, you get 7.7 grams of nitrogen. And if you want to do your check step, we go to our check step and we'd see that the mass that we were given has 2 sig figs. And the answer we get, because it was such a nice mass percent, also is given to exactly 2 sig figs. So our answer is just this, 7.7 grams of nitrogen. And we can also utilize these conversion factors to go the other way. We could have instead have been given a mass of nitrogen and asked, utilizing this mass of nitrogen, or like this mass of nitrogen came from the decomposition of ammonium nitrate, how much ammonium nitrate did you have originally? And you should be able to work back to that. Okay, and so we're just going to be utilizing either, this form of the conversion factor, or you flip it if you're trying to go the other way, always focusing on the fact that we're trying to cancel out units. In this case, since we're trying to get rid of massive compound, we put massive compound on bottom. Flip around if you're trying to go from element to compound. Shouldn't be too much of a surprise here. And if you'd prefer, you also could have done this as just, we're not going to use that yellow, it's way too hard to see. You also could have done it as 22 grams of NH4NO3, multiplied it by 0.35, and you would have gotten the same exact answer as you got here. Okay? And so this is just, our little mini lesson on finding what the mass of our ionic compounds and covalent compounds are, and then utilizing those to find moles of each of these different things. And then finally, once we know the moles of our compounds, either using the conversions in our little mass to moles to atoms chart to do, conversions that are pretty formalized, or if you're just doing a direct mass to mass, this is a very specific application. If you're just trying to go from mass to mass, you can use mass percent and you'll get there rather quickly. And so in our next lecture that we'll do on Tuesday, what we're going to talk about is utilizing these mass percents to actually work back. If you're given only the mass percents, work back and find out what the formula for the molecule is. And so I think we'll save that for Tuesday when we're a little bit fresher, but that's everything I have for you for this video.